Hello everyone, my name is Narendra. Our topic is anomaly detection on attribute network using constructive self-supervised learning. And our batchmates are Arvind and Pranay, and we are under the guidance of Raja Venkataraman sir, who is a senior data scientist. Our topic is mainly focused on anomaly detection and attribute network using the constructive self-supervised learning. First, let us talk about the anomaly detection and attribute network. It means the suspicious activities which are taken placed on the which are taken place in the network in a network. By using the context to self supervised learning, we can directly identify the which are the suspicious activities are going on the network. The main use of the context to self supervised learning is because the data sets which we provide are unlabeled, and it will directly detect the anomaly compared to the traditional method, where the traditional method try to reconstruct the data set and then find the anomalies. But using the contrast to self supervised learning, we can easily find out the anomalies on the larger data sets or the high dimensity data sets also. Attribute network contains of the node and edges, where the node represents with the attributes and the edges represent the relationships. Our application is mainly focused on the financial fraud. There are two types of anomalies: structural anomalies and contextual anomalies. The structural anomalies contains of the normal attributes and abnormal attributes, and whereas the contextual anomalies contains of the normal structure and corrupted anomalies. Let us take an example. The node represents the bank accounts or the user or a person, where the just represents the relationships. The relationships means we can say the transactions or the communication between the two nodes. Uh, Two nodes. The challenges which we faced on the anomaly detection attribute network are the diversity of the anomalies. There are several types of anomalies present in the in attribute network. First, let us focus on the main, or the transaction anomalies and the suspicious accounts, date, time, etc. And we have a and we do not have a labeled data sets. So we have to go with the unlabeled data sets, which we have choose a cola, which we have choose a cola method. And the most traditional methods are failed on the high dimensional data set. The deep autoencoder method deeply focused on the reconstruction and poor scalability. And next, the problem statement. The existing anomaly detection rely heavily on the labeled data sets and poorly perform on the large attribute network. And also, it mainly focus on the reconstruction part itself, but it does not directly detect the anomaly detection. For that, we need so we need a method that can be used on the unlabeled data set and integrate both the structure and attributes in a single method only. So we and detect the anomalies heavily and efficiently. Our objective is targeting directly on the anomalies using the nodes and the subgraphs, which will be which will be easy beyond reconstructing the data or errors. And again, and we are gather the information from the instant base and capture the contextual and structural anomalies. And after capturing the information, we embedded this information with the graph neural network, a constructive model for high dimensionality attributes and complex structure, ensuring the scalable detection by training on both batches of sample pair instead of the full graph. We use in this CoLA, in the constructive self-supervised learning, we use the batch-wise training, which will simplify the model to easily train the data set and have efficiency output. By delivering the superior performance state-to-state art, our results are benchmark data set. Next, coming to the literature survey, we have taken four research paper. The first is Akugolo 2015. He just started with anomaly detection techniques, have many limitation, hand graph features, and shallow models. And next we come to 2016 model, Peruzzi, introduced the graph-based methods, which will help us the network structure easy to identify the nodes and anomaly patterns. And next we come to you, 2020, have demonstrated the self-supervised learning pre-training model, which will go from the top to down of the tree. And next in 2022, in the same year, you also introduced a graphical constructive learning, which demonstrated the strong performing across graph level tasks. Research gap. Most existing anomaly detection methods, attribute networks, rely on supervised or semi-supervised learning, require label anomaly data, which is scarce and expensive in the layer application. And the next part will continue continued by my friend Arvind.
My name is Arvind. We go through the project scope. where the project is mainly focused on node level anomaly detection in attributed networks. So an attribute network is a graph where each node contains its features like about the information about the data, like the attributes, where it is also called as attributes. Uh, and also we have edge presence, like if we take F1 and F2 are the edge nodes, and the relationship between these is called as an uh, also and represented through the relationship is called as edge node relationship. So our goal is to identify nodes that deviate from normal behavior to by analyzing both their attributes and their structural position in the network. So this approach helps a lot. Like if we take mainly it is useful in the domains like the financial and the social network analysis, um, and also the communication and the cybersecurity systems. So in this, we assume a static graph settings where the network structure and the node features can be remain constant during the training. So our main scope is to design a project where it works without the labeled data, which is like unsupervised and captures both structure and contextual anomalies as well. So next we go through the methodology. Okay. So in this methodology, it is based on as CoL graph and also the graph neural networks. So the main we have the target node and the based on target node and the local subgraph to capture local relationships. So we use a GNN to learn the embeddings. So first, we construct contrastive instance, a node that and its the corresponding local subgraphs from a positive pair, and a node and an unreal subgraph from a negative pair. And next, we use the GNN for these embeddings, encode both with the node features and neighborhood structure. This allows the model to capture complex relationships in high dimensional data as it is and bidirectional, like it is we have done this in the like short data, not and then large data. Then we introduce a discriminator function to measure the agreements between the node embeddings and subgraph embedding, which has the high agreement indicates the normal behavior, low agreement indicates the potential anomaly, which is like error. So, and also finally, like if we take say notes are ranked based on three scores, these notes are higher anomaly, which indicates like as an outlier. And for the scalability, we train the model using the mini batch sampling instead of process the full graph, like if like a short data. So by this, which reduces the memory usage and allows the handle to train on learn or train on the large data sets. So in this, we by like current anomaly detection methods in attribute network general fall in two categories. Like if you take the shallow methods, we have MN and radar, and as well as the and in deep learning we have domain dominant spectral and networks where these attempts to reconstruct more features and graph structures. Anomalies are detected based on reconstruction error. While these methods improve performance, they still have limitations in respect to and their scalability. Now we go through the drawbacks of the existing system. Generally, this autoencoder based focused on the reconstructure later than directly identifying. First, it constructs, then later, and it also failed to like shallow methods cannot handle high dimensional data. So next, this is the proposed work. To address these issues, we propose a contrast to CoL self-supervised learning paper. The key idea is to instead of reconstructing data, we directly measure node subgraph agreement. Uh, our model uses like a GNN embeddings to capture both structure and attributes, which uses a contrast to learning to diffuse normal and the abnormal patterns. And next, we go through the block diagram. This is the structure of our contract call model. So firstly, we have the block. First, the input graph is provided consisting of nodes with attributes and edges, where we can see in the full graph where we have positive instant pairs and negative instant pair sampling, and the positive pair pool, and as it is transferred to the positive pair pool and the negative pair pool. These pairs are passed to the GNN. Then the GNN will be read out by like EI of which further it takes to the readout matter, and also contrastive loss function which separates the discriminator to it, and the BCA loss. After training an anomaly, the anomaly scoring model calculates scores based on the agreement values. Finally, the notes are ranked as we can see in the predicted score of positive pairs and the predicted score of negative pairs. So the pipeline ensures that the anomalies are detected based on their deviation from local context.
Hi everyone, Pranay here, and I'll continue with the results and discussions of our project. As you can see, our dataset consists of 20,001 nodes with 167 features each, representing the entities in the network. It includes over 234,000 transaction edges, showing the relationship between the entities. And the class labels are like it will tell whether a transaction is normal or anomalous. From the graph, you can see there are labeled transactions are 4,490 and the unlabeled transactions are 15,511. As you can see in the graph, normal transactions show a clear dominance over anomaly, and also transaction per time step graph, which indicates the transaction activities varies over the time, with anomalies appearing very less frequently. For the training our data, we have the for training, validating, and testing, we have divided our data set, and the number of transaction in each set is well balanced. For learning and testing, the proportion of anomalies is consistent across all the datasets, ensuring the unbiased model performance. During training, the model contrastive loss steadily decreased, showing effective learning. Where you can see here, first in the first 15 approaches, the loss was around 3.1104, but in the approach 135, the loss is 1.6325. And we have also using early stopping method for reducing the overfitting. And also, when it comes to anomaly scores, the model assigns an anomaly score for each and every transaction, indicating how unusual the transaction is. The statistical analysis shows that the anomalies generally have slightly higher scores than the normal transaction. An optimal threshold is selected for to separate the normal and anomalous transactions effectively. You can see here the we have used Jordan J optimal threshold, which is 0.2315. At this threshold, the model is able to identify a majority of anomaly cases. For a normal transaction, the model achieves high precision, means predictions are highly reliable. It also achieves good recall, successfully identifying most of the normal transaction. For anomalous transaction, the model achieves strong recall. Strong recall means it captures most of the anomalies. The model is able to detect the anomalies patterns in the data. Overall accuracy indicates that the model performs consistently across the datasets. And the model performance matrices, you can see ROC-AUC and also the PRAUC. ROC-AUC is around 0.6573 and PRAUC is 0.1363. The ROC-AUC score shows that the model performs better than the random classifications. It demonstrates the model's ability to distinguish between the anomalous transaction and also the normal transaction. The PRAUC score reflects the model's effectiveness in identifying anomalies in imbalanced data. And also, the anomalous score distribution shows how scores are distributed between the normal and the anomalous transactions. The threshold line, you can see here that the threshold line clearly indicates the decision bound used for classification. Based on the threshold, we can tell whether it's an anomalous or a normal transaction. The training loss curve shows a steady decrease over the approaches from 0 to and 140 approaches. You can see like it is been decreasing, which indicates that the it is successfully learning. The ROC curve demonstrates the model's ability to separate the classes across different thresholds. The precision recall curve highlights the model's performance in detecting the anomalies effectively. And overall, I can tell that the model effectively learns transaction patterns and successfully identifies anomalous behaviors using contrastive self-supervised learning.